Good morning, statistics scholars. Today is Tuesday, still Tuesday, April 29th, around 11 o'clock. I wanted to continue our discussion and our lecture on this week's chapter on related or paired sample t-tests. I'm recording this video for both sections of my statistics class in on campus and also at Donovan because we're at the same point. So as I review yesterday in both classes, first of all, I just want to say how proud and impressed I am at your ability to cover and to process such advanced material. We just started hypothesis testing a couple of weeks ago with chapter 7, which really introduced the idea of testing a hypothesis, the null and the alternative, establishing or using a new formula, which is the standard error, and using that to determine whether you're going to accept or reject a null hypothesis based on what your alpha is. So I'm really impressed with the material that we covered. We looked last week at a one sample t-test with the Waymo car scenario. And this week we looked at a pre and post test. And I introduced in yesterday's lecture the idea of time. Time one and time two. Time one happens first, time two happens later. And so when you're looking at, or if the research project or the research purpose is to look for a reduction, as in the example for migraine headaches, if you're trying to have less migraine headaches, you want to look at a reduction. So in those time periods, T1 and T2, the formula to find out the difference is time one minus time two. And that should get you a data of difference that looks at the decrease of symptoms. Or when we're looking at an increase, as in the pre and the post test scenario, where we test you first in time one, and then we do an intervention, then we test you again in time two. In that instance, the difference is calculated by T2 or time two minus time one, and that should get you the increase. But in any event, we're looking at the difference, and I'm really impressed at how you took that fairly easily. There may be some questions, some things that are um, not quite clear, but keep practicing. What I want to focus on today in this brief lecture is confidence intervals or confidence intervals, because that's an area that really seems to trip up people a little bit until they get used to it. So I'm going to use an example in the textbook and talk about what you need to run the confidence interval. And so far, we've been running t-tests only looking at the t statistic as determining whether to reject or accept the null hypothesis. In this example today, I'm going to run through a lecture or an example in this lecture that we're doing hypothesis testing, but we're not going to use the t-test to determine it. We're going to use the confidence interval to determine whether to accept or reject the null hypothesis. And hopefully, this helps clarify what the confidence intervals are. And then I'm going to run through a brief example in the exercises to show you the pieces that you need, the elements, the components that you need to run a confidence interval. Basically, you need a couple of things. You need the standard error for the confidence interval. Well, let me start in order. You need the mean, because you're going to plus or minus that. So you need the mean of the sample. Then you need the critical value for a two-tailed test. And to get the critical value for a two-tailed test, you need to know what the alpha is, and you need to know what the n size is, because that tells you the degrees of freedom. But in some cases, if you don't know the n, but you know the degrees of freedom, you know what the n is because you need the n to figure out the standard error, because the formula for standard error is standard deviation divided by the square root of n. So keeping those elements in mind, let's take a look at the example on page 123. It's about friendliness. And I'll read through it very quickly and then we'll work it out on the map. Friendliness. You hear that the national average on a measure of friendliness is 38 points. So that's what we're measuring it against. You want to know if people in your community are more or less friendly than people nationwide. So you collect data from 30 random people in town to look for a difference. We'll follow the same four-step hypothesis testing procedure as before. All right, so we first start by stating the hypothesis that there's nothing happening. The null hypothesis is there is no difference in how friendly the local community is compared to the national average. And so the null hypothesis is mu equals 38. And then we establish the alternative hypothesis. There is a difference in how friendly the local community is compared to the national average. And in this test, we're looking for either greater than 38 or less than 38. We just want to see if it's different than 38. We don't care which direction. So that's when we're using not equal to. So that would be a two-tailed test. So then we find the critical values. We need our critical values to determine the width of the margin of error or the standard error. We assume that the significance level is 0.05 because it always is unless we specify, which gives us or conforms or confers to a confidence interval of 95. 0.05, 95. 0.01, 99. And so we go to the t-table to find a two-tail critical value because this test actually is a two-tail. So most of our tests so far have been a one-tail in the t-test. But when we got to the confidence interval, we had to select a critical value for a two-tail test. But here, our test actually is a two-tail. All right. So if we know we randomly selected 39 people, so the n is 30. I'm sorry, we randomly selected 30 people, so the n is 30. And if the n is 30, the degrees of freedom are n minus 1 or 29. And so we would go to the t chart. Let's see if I can go very quickly there. And look in the two-tail area right here. We're going to go all the way down for 0.05, because see, we're in two-tail, to 29, and it's 2.045. Hopefully that makes sense, right? Let's go back. So 2.045, that's how we got the critical value for a two-tail test right there. And then we calculate the confidence interval, but first we need the standard error. The standard error is, the formula for that is standard deviation divided by the square root of n. So they told us here in this example that the standard deviation is 5.61. So we're going to use that to calculate the standard error. So this is how you see that right here, 5.61 divided by 5.48. That gives us the standard error of 1.02. And then we use that to fill out the example. So all of the answers are here, and that's fine. I really think that it's important for you to, particularly when there's an example, to go through the example in the book so that you get the moves in your fingers so that you don't feel intimidated. And that way you can sort of do the exercise, do the calculations, and then check back to make sure you're okay and make any corrections because it's very easy to drop the ball and forget something. All right, so I'm going to work it out. You can still look on page 124 as I work it out. But what my goal is here is to demonstrate and to show you how we're using a confidence interval to tell us whether to accept or reject the null hypothesis. Up until now, we've been using the t-test and we draw out our curve, we make the rejection zone, and if the t result or the t obtained is in the rejection zone, then we reject the null hypothesis. If it's not, then we fail to reject. But we can do the exact same thing with a confidence interval. So let's take a look at that. Right, so let's start with we're looking at friendliness. Make sure you can see that. And we start with the null and alternative hypothesis. The null hypothesis is there is no difference in how friendly the local community is compared to the national average. And there's some survey, some way that they got the national average. And the national average that we're using is mu equals 38. Okay. So now let's run our alternative hypothesis. And our alternative hypothesis, we're just trying to see is it greater or less than? Is it different? So maybe if it's greater than 38, then the people in the local community are more friendly than the national average. That's a neighborhood you want to live in, right? If it's less friendly than the national average, that perhaps means that people are a little not nice, and maybe that's a community that you don't want to live in. So there is a difference. In how friendly the local community is compared to the national average. And we don't care, we're looking to see if it's greater than or less than. So its mu is not equal to 38. But we could also write it as mu is greater than or equal to, or greater than or less than 38, sorry. And in the event, it's a two-tailed test, right? So let's gather some other information. Our n size was 30. We asked 30 people randomly, which means the degrees of freedom are 29. And we set the alpha as 0.05, which means we're going to do a confidence interval of 95%. And since we're doing confidence interval, it is a two-tailed test. And that we already found out that the critical value was 2.045. So it's negative 2.05, and positive 2.05. If that looks the correct way for you. All right, so we remember that the confidence interval formula is the mean, in this case the mean is 38, plus and minus the critical value for a two-tailed test for whatever the degrees of freedom are, for whatever the alpha is, and we determined that that was 2.045, times the standard error. Okay, but they didn't give us the standard error. They, however, did give us the standard deviation. The standard deviation is 5.61. So if we have the standard deviation, we can figure out what the standard error is, because the formula for standard error is the standard deviation divided by square root of n, right? So if we fill that in, 5.61 divided by the square root of n, and n happens to be 30, right? So if we figure that out, 5.61 divided by the square root, second key and square root of 30. That gives us 1.024. So we can round it down to 1.02. Right, so that's the standard error. Right. So now we know what that is. We know what the standard error is, and we also know what the critical value is. The critical value we already found out was 2.045. And we know what the mean is. The mean is 38. So we have all the elements we need to figure out, to calculate the confidence interval. So let's just fill it in. I like to do the lower first, right? The lower is 38 minus, because we're doing lower, 2.045, and I'm putting the parentheses around that because we have to calculate the product of this, and then subtract it from 38 times 1.02. That is the lower, and the upper is 38, and it's all this plus 2.045 times 1.02. Okay, so let's figure out the upper. 38, I'm sorry, the lower, minus, put the parentheses around, 2.045 times 1.02, close the parentheses, it is 35.91. Let's figure out the upper, 38 plus, parentheses, 2.045 times 1.02, 40.085, so we can go to 40.09. Because at 5 we can round the 8 up to 9. Okay, so our 95% confidence interval to report it equals bracket 35.91, that's the lower, 40.09 is the upper. Okay, so that's the result. Now let's take a look at what we're testing it against. We're testing to see if it is 38. If it's 38, then there is no difference. The confidence interval tells us what the test is likely to be. We're 95% confident that of the data that we collected from the 30 people, where the standard deviation of that was 5.61. They didn't even give us, they gave us 38 as the, oh, sorry. Look at that, I made a total mistake. 38 was our test statistic. We're actually testing it against not 38, but when we surveyed people, the mean was, that was the mu. The mean was 39.85. So let's just do that again. Lower, we have everything we already need, but it's 39.85 minus 2.045 times 1.02, and the upper is 39.85 plus 2.045 times 1.02. See, I didn't make mistakes. I don't even try to hide them anymore. Okay, so you just run it again. 39. Well, first let's talk about this. We're testing it against 38, and when we surveyed 30 people, the average was 39.85, which means it is higher than 39.85 is higher than 38, but only slightly. So can we say definitely that it's higher or that it's different than 38? That's what the confidence interval is going to tell us. It's going to tell us what, based on this data that we collected with standard deviation of 5.61, what is likely to be the range, the lower and upper range of the community that we sample, and then we can test to see if 38 is in there. So 39.85 minus, again, put the parenthesis around, 2.045 times 1.02 equals 37.76. We're going to do the same thing, 39.85, but this time the upper region, parentheses, 2.045 times 1.02 equals 4194. Okay. It didn't really affect the outcome too much. It just was not the right answer. So our 95% confidence interval is 37.76, 41.94. So the range, we're 95% confident that the people that we surveyed, the 30 people that we surveyed, is somewhere between 37.76 and 41.94. But how do we decide whether to accept or reject the null hypothesis? The null hypothesis is that it's 38. If the null hypothesis fits within this range, and it does, then 38 is one of the possible values. So that means we cannot reject the null hypothesis. We have to fail to reject the null hypothesis. And that's what it says in the example. It says that based on our sample community, let me write it out. Based on sample community, data collected. I always like to describe all the data. N equals 30. The mean equals 39.85. And the standard deviation equals 5.61. The confidence interval, provided evidence that the local community is no different than the national. Again, let's fail to reject. And the 95% confidence interval equals 37.76, 41.94. Fail to reject. Hopefully that makes sense. You can practice that example yourself. Maybe even see if you make the mistake. Use the turn off the video and go work through the problem yourself. Get the answers or the data or the components and try to work it out yourself. What I want to do now, however, is work through the exercise of number 4, because I think this gives you a good idea of how to sort of view a confidence interval from many different facets or many different vantage points. So we focus on exercise number 4. There are 4 problems. We're going to work through all 4 problems. I'll work through them so that you get a sense of how they work. And again, I recommend that you do this yourself so that you get it in your fingers or follow along as I'm doing it. Don't just watch. Take out a sheet of paper and work with me on the map. All right, let's go back to the map. But here, I'll write out the pieces, but for each element of the problem, A, B, C, and D, the sample mean is always 25. They're just asking us to construct the confidence interval. They're not asking us to reject or accept or fail to reject the null hypothesis. But in A, the n is 25. It also is 25 in B. The standard deviation for A and B is 15. But for A, we're constructing a 95% confidence interval. But in B, we're doing a 90% confidence interval. This is the first time we've done a 90% confidence interval. We've always done 95. We haven't even really done a 99. So we're doing a 90, which all of the pieces are the same. If you understand how to do a 95% confidence interval, you also know how to do one for 90 or 99. But look in problem C, they don't give us the n size, but they give us the degrees of freedom. If you know the degree of freedom, you know what the n is. Just like if you know the n, you know what the degree of freedom is. You just have to go the other way. And in D, they give us the standard deviation, but they don't give us anything else except the degrees of freedom. So let's talk through how to make those, fill in those gaps and create the answers. Let's go back to the map. So we're looking at problem 4, which is build confidence intervals. Okay, let's start with the m is always 25 for each of the problems, right? Let's start with, well, let's write on the side that the formula for confidence interval is the mean plus and minus the critical value for a two-tailed test, which is always for a confidence interval, times the standard error. And the formula for standard error is standard deviation divided by square root of n. You keep this information in your pocket as you work through problem 4A, 4B, 4C, and 4D. You know what you need versus what you have, and then you can figure it out. All right, so let's look at A. For A, the n is 25. It should be a small n, but anyway. N is 25, which means the degrees of freedom is 24. The standard deviation is 15. And we're doing a confidence interval of 95, which means the alpha is 0.05. All right, so we have everything that we need to work it out. So let's do the formula. We want the lower first. The lower is m is 25, so minus, let's do the upper. Upper is also 25, this time plus. Now we need the critical value. We need the critical value for a degrees of freedom 24, for an alpha of 0.05, but for a two-tailed test, right? So if we go very quickly to we want two-tailed 0.05 because we're doing a 95% confidence interval, and we want degrees of freedom 24. To go all the way down to 24, it is 2.064. 2.064 right there, right? So 2.064. 2.064. Now we need to know the standard error, which we don't. But the standard error formula is the standard deviation divided by the square root of n, and n is 25. So if we figure out what the standard error is, we can figure out what we're multiplying the critical value by. So 15 divided by square root of 25 equals 3. So that's what we're multiplying it by. All right. So 25 minus 2.064, which is the critical value, times 3 for the lower. Upper is 25 plus 2.064 times 3. All right, so I'm going to do it the long way the first time, and then I'll show you a shorter way. 25 minus 2.064 times 3, 18,808, so 801. We're going to round that up to 81. And 25 plus 2.064 times 3, 3119. So the 95% confidence interval, to write it out, is 18, 81, it's an 8, and 31, 19. Simple, dimple. That's the answer for A. All right, let's move on to B. For B, they say the N is 25 again. The standard deviation, which means the degrees of freedom, is 24. The standard deviation is still 15, but this time they want a 90% confidence interval, which means the alpha is 0.10, which we haven't done yet. So the only thing that's different about everything is the same. We're still using 25. We're still using 24 as the degrees of freedom, but the alpha, meaning the critical value for this problem, is going to be different. So let's very quickly find our... So we want a two-tailed test in the two-tail area, but here we're going to look for 0.10, which we've never used before. So go down. This time we're looking for, see, we used 2.06 for the last time. This time we're going to use 1.711 because that confers to 10% or 0.10 alpha, or a 90% confidence interval. All right, so if we go back, let's work it out. So the lower is 25 minus the upper is 25 plus, but this time we're going it using the critical value of 1.711 times, and we're still using the exact same standard error, 3. Right? Because still the standard deviation is 15 and the N is 25, so that means the standard error stays the same. Just the critical value changes. So let's see what that does to our answer. So here's what I want to show you the easier way. We could figure out what this is, meaning 1.711 times 3. It's 5.133. Now we know that we can just subtract 5.133 from 25 and then add 5.133 to 25, right? So 25 minus 5.133 is 19.87 because it's 867, 87. And 25 plus 5.133 is 30.1313. So this time our 90% confidence interval is 19.87, comma 30.13. That makes sense, right? Those two were fairly easy. Let's take a look at C, which is a little bit difficult because they're giving us less information and allowing us to figure it out. In this instance, they gave us the standard error of 4.5. So we know that. We don't have to figure it out. So that's going to be right here, 4.5, because that's where the standard error is. And they also give us the alpha of 0.05, which means we're going to be doing a 95% confidence interval. And they give us the degrees of freedom of 20, which now we know if the degrees of freedom are 20, what is the n? If degrees of freedom are 20, n must be 21. All right, let's see how we use that to figure out the confidence interval. Lower, upper. For every problem, the m is still 25. So 25 minus, 25 plus. Now we need to figure out the critical value. We know that we need a two-tailed test. We know that it is 0.05, and we know what the degrees of freedom are, right? Yeah. So let's go over to we want a two-tailed test for 0.05 for degrees of freedom 21, 205, 21. Or 20, sorry. Degrees of freedom 20. There we go. 2.08, 2.086 is our critical value, right? 2.086 times, and we know that our standard error is 45. If we want, we can figure out what this is, 2.086 times 4.5, which is 9.387. You want to use the whole thing, right? You want to use the whole thing in calculations, but you round for resolutions or results. We're going to use 9.387 so that we use the entire result when we're subtracting and adding it to the mean. So 25 minus 9.387. Here is 1561. See that's the difference. This is the result, so we're going to round it. Here we're using it to continue some calculations. This is the result. We're not calculating anything beyond this. 25 this time plus 9.387. 34, 39. Yep. So our 95% confidence interval is 15.61, 34.39. Right? Fairly simple. All right, let's look at D, which is a little tricky. D, they gave us the standard deviation, which is 12. They gave us the degrees of freedom, which is 16. That means that the n must be 17, right? So, lower, upper. We're still using 25 minus 25 plus. All right, so what is our critical value? They haven't told us anything, so it must be 0.05, which means we must be doing a 95% confidence interval, right? And so we know what, we also need the standard error. Well, we know that the standard deviation is 12. The formula for standard deviation divided by the square root of n. And they didn't give us the n, but they gave us the degrees of freedom. So we know that the n, if the degrees of freedom is 16, the n must be 17, right? So we're going to figure that out. 12 divided by the square root of 17 is 2.91. Yeah, 2.91. All right. And now we need to figure out what our critical value is. We want a critical value for a two-tailed test for degrees of freedom 16 for alpha of 0.05. Two-tail 0.05, degrees of freedom 16. 2.120. That's what we're multiplying, or we're subtracting, or multiplying it by the standard deviation, and we're subtracting the result and adding the result to the mean. Let's go back. Hopefully this going back and forth has been useful. So our critical value is 2.120 times 2.91. 2.120 times 2.91. Let's figure out what that is. 2.120 times 2.91. 6.1692. Let's use the whole thing. Okay. 25 minus 6.1692. 18.83. 25 plus 6.1692. 31.17. 31.17. Right? So our 95% confidence interval for D is 18.83 and 31.17. And that's that. How was that? Hopefully that made sense and you were able to follow along. What I love about the videos is that you can stop them, you can rewind them. If you find that I made a mistake, I make mistakes all the time. Tell me where they are. If you find a mistake, defend it, and I'll give you 25 extra points. I don't think I made any mistakes that I didn't correct. I made that big mistake at the beginning. But hopefully this sets you up for understanding confidence intervals. They work the same whether we're doing a one-tailed test or a one-sample test or a paired sample test. And we use, at the beginning, we use the confidence interval to tell us whether we're going to reject or fail to reject the null hypothesis. If the test value in the null hypothesis is within the confidence interval, that means it's one of the possible values. You cannot reject the null hypothesis. You have to fail to reject it. So hopefully this gives you something to help you practice in chapter 9 for paired samples and prepares you for next week, where I will continue this in a different lecture on independent samples, which is a little more complex, but not a little more complex, not very complicated. It's the same idea. It's just we're doing things a little bit differently because in a one sample t-test, we're just testing it against one sample, one n. In a paired sample, although there are two times, time 1 and time 2, essentially we're still only using a single difference, XD, but in independent samples, the two samples that we can test can have different sizes. So we have to weight the sizes. One could have an N of 30, and the second group could have an N of 45. And so if that's the case, we have to pool them together so that we can make a good comparison. All right, having said all that, good luck, and I'll miss you. I'm excited to see all the statistics that you find this week. Don't forget, you have a quiz that's due on Saturday. I'm not going to change the date. So get that done. I have opened up all of the previous quizzes from chapters 1 to 8. So if you didn't finish those, you do get some extra time. But moving forward with chapter 9, all the quizzes need to be done by Saturday night. All right, good luck. See you soon.
And find your peace of mind. Return to paradise. Velvet moon above. Evil turns to love. Love evermore. Come with me and find your peace of mind. Return to paradise.